Section 5 in Chapter 11 focuses on linkage and gene maps. And we've been kind of going along with the idea of independent assortment, where it doesn't matter what the organism will get, the offspring will get for wrinkled versus round seeds. That doesn't necessarily influence the seed color. But we have to remind ourselves that it is actually the chromosomes that are going to go through the independent assortment. They are what actually separate from one another. We remember back to crossing over during meiosis. Remember, we have the sister chromatids and we have this crossing over, but you're actually having these individual chromosomes that are separating. Because it's the chromosomes that are separating, we have to look at where the genes are located. So genes that are on each of those chromosomes often are going to get passed on together. So what we call linked genes are genes that are going to be on the same chromosome. So you might have one chromosome that has the genetic information for hair color and eye color and maybe skin color or whatnot. Those are going to be linked if they're on the same chromosome. And we still get that variation because of the crossing over during meiosis. So even though we have specific genes and alleles on each chromosome, when crossing over occurs during prophase 1, we are going to get some different variations in here. So what does this actually mean? Well, again, when we do our dihybrid crosses or our Punnett squares, there's stuff that we expect that we get. Remember, those are based on probability and those possible outcomes. But again, when we are dealing with linked chromosomes, if some are linked, often we're going to get them together. So they might not follow the rules as nicely as we would expect them to. Gene maps help us determine where these might be located and help us understand if genes are possibly linked. So one thing to do is look at the probability of crossing over events occurring between each of the genes. So we can see if there's any issues with our typical Mendelian genetics and see, wait, are some genes being linked? And maybe that's why we're not going to get the probability that we would expect. Thinking back to some of you working on your genetic traits, where some of you, the probability in your brothers and sisters, it doesn't quite make sense why maybe there was 4 of you that all got a specific trait when maybe only 1 out of 4. And this has to do with this gene linkage. So what we're going to do is actually look at some different numbers here. So the gene maps, we have the genes for A, B, C, and D, and they're located on the same chromosome. If crossing over occurs between each of these chromosomes, how could we maybe draw a gene map to show where those genes might be located? Well, you're always going to want to look at kind of the highest number for that. And we know between A and C, we have a 30% chance that this crossing over is going to take place. So we know that they're most likely further away from each other in the sense on the gene map because there's a higher probability that those are going to get separated. B and C has a 9% and A and B has a 23%. So if you were to look at kind of where those might be on location, I drew the A down here just so they're a little bit closer, but we have this idea that A is further from C, and that's why there's a higher likelihood that at some situation that those are going to be crossed over separately. Whereas B and C, the possibility of crossing over occur to them is quite smaller. So the lower percentage means they're likely located closer together on the chromosome, and that way when the crossing over occurs, they're not split from that. Again, we can kind of look at some different examples here as to what would happen when A, B, C, and D are located on the same chromosome. Again, we want to look at the larger possibilities or the larger percentages to get an idea of where they might be. So we know between B and C is our largest kind of thing in here. And again, this might take a little playing around with actually seeing where these might go. So I'm just going to try and bring some of these down so we can see them. All right, so I'm just going to put, and I have to format that, bring it to the front here. Okay, so if I'm saying C is right there, what does that mean about where B might be? B is probably going to be a little bit further away from it because we have the higher percent. Okay, and we're just going to try and cover up some of the things that I have. Okay, so B and C, there's a almost 30% chance that when the genes are crossing over that those are going to be separated. Notice A and B must be really close together. They're going to have a 7%. So maybe my A comes possibly right here, and our D, again, is closer to the C. If we had more information, we'd understand kind of how the rest are related, but we get this idea of what kind of the percentages are between them and where possibly are they related. That way, when we're looking at those dihybrid crosses, those Punnett squares, we can kind of see, wait, why would we not expect the probability that those are going to predict for us? And a gene map just gives us a little bit of information to say, oh, okay, these are located close together, so when that crossing over occurs, they're generally going to be linked together. So in this case, if the crossing over occurs between D and A, we know A and B are going to go together. So if one of them gets A, they're also going to get B. Same for C and D. They come as a pair. And this can kind of help explain some of the variations or the surprises that we see in our typical Punnett square genetics. This ends the lesson, and this ends all of Chapter 11.